Hmm. All right, here we are. So these are very unusual circumstances, of course, but the way it looked even late last night, it was snowing pretty hard up here. Plus, I'm getting a little sniffly here, so I thought it might be a good idea to do this online. Surprisingly enough, we haven't had to do it yet this semester. Most springs, it turns out to be necessary to have an online class at least once or twice. But this year, the weather wasn't quite as awful as usual, so this will be our first, and I'm sure it'll be our last, unless there's some horrible windstorm or something that knocks down all the trees, which does happen periodically in Purchase. But anyway, so what we're going to do is go through the two problem sets for chapter 4. And of course, when we're done, I'll be posting these on Moodle. And then if there's time, we'll at least take a peek at chapter 5, I guess. I think that we were pretty much done with 4. We may have just started to take the quickest imaginable peek at 5. So we'll carry on from there. Now, I'm starting to forget. I know I must have written this down somewhere when our next tests will be, but it won't be next week, that's for sure. And it might not even be the week after that. So we don't have to worry about that just now. But later on, I'll look it up in my notes and I'll post an announcement as far as the date of the second midterm is concerned, because it is entirely based on chapters 4 and 5, not 1, 2, and 3, just 4 and 5. So that means that it's coming up reasonably soon. Of course, it can't happen before the spring break because this is our last meeting before the spring break. If you recall, our spring break is next week. Just go get the schedule here. Let us double check this real fast. And we will confirm. Yeah, spring recess, the 18th, that would be this coming Saturday rather. So so in other words, we'll not meet again until 2 weeks from today. Okay. Oh, all right. I'll get back to you about that later on. I'll look through my emails and see what happened. I'll tell you what, let me write this down somewhere so that I don't forget. All right. So here, let's do it. So I'm going to open up the questions for chapter 4. There's 2 of them, by the way. And so this is number 2. Let's get number 1 open. So what are we doing with these? All right. So in these cases, we're trying to find the formula or equation for an exponential function that passes through these 2 points. Okay. Now, as we saw in the classroom the other day, these functions can get really, really messy. And so what we have to ask ourselves is, what exactly are we doing here? Well, remember, the standard equation for an exponential function is f of x equals ab to the x power. A is the initial value. And b is 1 plus the growth rate. Okay, so, oh, Jesus, hold on. So as you can see, I'm using a tablet. Every once in a while, my finger hits the wrong button and it makes a mess. So there we go. So that means we know 2 things. Oh, Christ. Hold on 1 second. Yeah, every once in a while it gets like this. Yeah, there we go. Okay. Yeah, if I'm not careful with this thing, it just makes a mess. So for the first point, 1,6, this is of course x, this is f of x. So what that means then is that this tells me that 6 equals a b to the first power, or very simply, 6 equals ab. Which by itself doesn't tell us enough to satisfy the requirements of this equation. We don't have either a or b, but what we can do though is use the second point and come up with another expression. And that will give us enough information to solve for this equation. Okay, in other words, we need to solve for 2 unknowns, which is what we have here. We need 2 equations. Okay, so this one is telling us that 750 equals AB cubed. And that's all we know. Okay, so what do we do? So what we should probably do, remember, we're trying to solve these simultaneously. We're going to use the method of substitution. So why don't we do this? And there's many different ways of going about this, by the way. We'll start with 6 equals AB. And we'll divide out the b from both sides. So then for this other equation, we can replace the a with 6 over b. Now, since actually we can rewrite this now as 6b cubed over b, and the ratio b cubed over b is simply b squared. So it's 6b squared. Now we can simply divide both sides by 6. And if you divide 750 by 6, you'll get 125. Then we take the square root. Now, unfortunately, this is not an integer. Okay, 125 is not a perfect square. So what we can do, though, is note that this can be written as 25 times 5, or radical 25 times 5. And that means that 5, oops, no, I did this, I'm sorry. I left this out. There we go. There we go, we're good. So we now have the actual value of b. So what remains to be done is find the correct value for a. For that, we can go back to this equation, 6 over b equals a. So that means we have 6 over 5 radical 5 is a. Now, you can leave it like that, but in practice, we try to avoid having radicals in the denominator. So the strategy for eliminating that is to do this. We're doing a process here called rationalizing the denominator, which basically means that you're turning the denominator into a rational number, which means not a radical. So you're going to have 6 radical 5 now that means when you multiply radical 5 by itself, you're going to end up with 5. And so ultimately your result is 6 radical 25 over 25 equals a. And then now it can't really be simplified any further. So therefore, what you have here, finally, when all the dust settles, since that's our value of a, remember b is 5 radical 5. That means the final result is 6 radical 5 over 25 is multiplied by 5 radical 5 raised to the x power. Now, if you want, although it's not necessary, you can actually calculate the approximate values of these numbers. For example, if you take radical 5 times 6 and divide that by 25, that turns out to be about 0.5367, let's say. And then 5 radical 5 is approximately 11.18. Raised to the x power. And if you're dying of curiosity to know what this thing looks like, we can also go to our old friend Symbol Lab. And just to keep it simple, we'll use the approximation y equals okay. 0.5367 times 11.18 raised to the x power. And let's see what the graph looks like. Okay, well, it's your typical exponential function. The interception, see where that's where it intercepts. That is what we call the initial point. That is our A. So if you're only considering values in the first quadrant, this is where X begins. And then, as you can see, it grows like crazy. In fact, you can see the growth rate is rather rapid. It's quite large. So that's it. That's how this is done. All right. So the rest of these are exactly the same. So why don't we go to the next one? All right. Let's see what's next. By the way, if anybody didn't pick up their exams, they're in my office. If I happen to be there, like on Thursday morning, for example, you can come and get it. But you don't need to because these scores are all posted in Moodle. I mean, you can you can have it, but I mean, the score is already in Moodle, so you don't have to worry about it. All right. So once again, we have X. X. So that's the information that we have from the first point. Oh, by the way, I just want to point out that if you're not convinced that your results are correct, you could take your initial 2 points, for example, here 1,6, and plug it into this expression and see if it does, in fact, give you the correct value. And you'll see that it does. But you can double check these results by substituting one of your points into this function and seeing what you get. We're not going to do that here, but you could if you chose to do so. Now, for 2,20, with X and f of X. Okay. So once again, we'll replace the information we have. Okay, so now we can approach this in a few different ways. We got 2 pieces of information. Let's put them together in one convenient location. So what we could do, for example, is take the 2,000 equals AB and divide both sides by B. And once we have that, we can replace that A with 2000 over B. Okay, let's rewrite it slightly. And of course, B squared over B is just B. Now we can divide out both sides by 2000. So the ratio of 20 over 2000 is 0.01. That's kind of nice. It's not a messy radical. It's just 0.01 or 1/100. So that means the growth rate is negative. I mean, because remember, B is 1 plus the growth rate. So this one will be decaying very quickly, actually, because B is so small. And then once we have B, we can go back to either of these two expressions. We can pick, let's say, well, let's do 2000 equals AB. So if you divide this by 0.01, it's the equivalent of multiplying by 100. Okay, so to go to your calculator and take 2000 and divide by 0.01, you'll get 200,000 equals A. Of course, we already know that B is 0.01, so the final result is right. And again, maybe it would be fun to look at this in Symbolab. But whenever B is less than 1, that means the function will be decaying rather than growing. So we have 200,000 times 0.01 to the x. Ooh, so you can see, yes, it's falling off very, very rapidly. The intercept is the 200,000. And then after that, it falls off very, very quickly so that it's essentially 0 by the time we get to 1. So again, this could be maybe the half-life of a radioactive element or something like that. All right. So let's see what we have here. We'll start with the first one. So this tells me that 6 equals AB to the -2 power, and 3, 1 means that one equals AB to the 3rd power. So both of these are kind of messy. So how about this? Let's take our first, let's write them together. We'll take this first one and just rewrite it as 1 over B cubed is A. Now, if you prefer, if you think it might be simpler, you can rewrite this as B to the -3rd equals A. Then we can replace this A with B to the -3rd. b to the minus second. Now remember the way exponents work. This is going to be b to the minus 3 minus 2. Now, algebraically, I think it might be easier here just to rewrite this as 1 over b to the 5th. So you can see that we can multiply both sides by b to the 5th. And then divide both sides by 6. And then I need to take the 5th root of both sides. Wow, what a mess. That's my b. Yeah, this one is pretty ugly. So we can now go back to our other expression. 1 equals ab cubed. Okay, now that means that 1 equals a. And then we have all of this. The entire expression is cubed. Ooh, okay, so that means 1 equals a 1/6 to the 3/5 power. So now we're going to divide this. And now we could leave it like this, I suppose. But why don't we do this? Okay, so let's go back and run through this one more time because it was such a mess. I'll tell you what, on the test, I'll try to avoid these horribly messy ones. So we had 6 equals ab to the minus 2, 1 equals ab cubed. A is 1 over b cubed, or b to the minus 3rd. We bring that over here. 6 is b to the minus 5th, or 1 over b to the 5th, multiply, divide by 6, take the 5th root. And since 1 equals ab cubed, yeah, that's it. Okay, so just a quick reminder, b is 1/6 to the 1/5 power. I think we're definitely going to figure out the values here. Okay, so for this one, why don't we do this? Let's figure out the approximate values of these two. 1/6 raised to the negative 3/5 power is about 2.93. And 1/6 raised to the 1/5 power is approximately 0.6988 to the x power. So again, if you notice, b is less than 1. And so that indicates that this one will be decaying rather than growing, because that means the growth rate is negative approximately 0.3012. Okay, so let's grab Symbolab.
Professor,
Yes.
can you just explain the growth rate? Like, You were saying what was less than one? Like,
That's
I
right.
was just wondering if you can explain that really quickly.
Yes.
Thank you.
So that's the growth rate plus one, which I'll substitute here. If I should now subtract one from both sides. So this could be, for example, I don't know, let's say you bought an incredibly expensive car and it depreciates at the rate of 30% per year. That's very high for a car, but the idea is that the value of this item is shrinking, or, or it could, like I said, sometimes you see this used to represent the half-lives of radioactive elements like uranium. And what it's basically showing us is how quickly the amount of radioactive material is decaying and being converted into lead. So when I graph this, it'll be going down very rapidly, as a matter of fact. So let's go get Symbolab and confirm this. We have 2.93. The B is 0.6988. And so, yes, it cuts through 2.93 and it falls off very, very rapidly. Very rapidly. Now, in a normal situation, let's say you had a car and it starts out being worth $25,000. And let's say that every year the value falls by about, let's say, 8% due to wear and tear. This would be a more normal scenario for something like that. It's falling off, but I mean, it's not like after 20 years, the car still has some value. Oh, well, that might be pushing it, but so in other words, whatever you put here, it's like if I put 85, that means it's losing 15% of its value every year. And so you could predict what the car would be worth after a certain number of years by looking at this graph. Right. So in other words, after 10 years, it's worth less than half of, well, it's worth a lot less than half of what it started out. That looks about right. All right, one more. And now we're going to be looking at interest rates. Now, this is interesting because this is a real world application of what we're doing here. If you assume that money is or interest is compounded continuously, then we actually are experiencing exponential growth with our bank account. Or if you're trying to save money, well, all right, we'll get to that in a few minutes. First, let's finish up this last one. So this tells me that 1 equals AB to the cubed. And then for the point 5, 4. This means that 4 equals AB to the 5th. All right, well, this is not going to be, the result here is not going to be a couple of integers either. But we can handle this. So why don't we start by taking this one and rewriting it as 1 over B cubed equals A, or B to the minus 3rd equals A. And then this A is plugged in over here. Ooh, wait a minute. We might have some nice numbers this time. Because look what happens. B to the minus 3rd, E to the 5th means that we have 4 equals B squared. And so we just end up with two, what do you know? We finally got a nice one. It's about time. Okay. So what about now over here we have 4 equals AB to the 5th. And that means that 4 equals A times 2 to the 5th. Which is just 32. 4 over 32 is A, which is just simply 1/8. Well, I like this one. It couldn't get any simpler. Oh my God, they should all be like this. So the final result is that 1/8, 2 to the X. Now here the growth rate is 100% or 1. So it's going to grow very quickly, starting at 1/8. So let's look at this in Symbolab. Oh, I'm looking forward to this one. A nice straightforward. Oh, what's that? What did I do? That's a 3. It's an 8. Okay, 1/8, 2 to the X. And so, yeah, it starts at an 8 and it grows very, very quickly. Now, if this was a traditional, let's say a bank account where the interest rate is, let's say 5%, then you would have 1.05 here. And let's say you start with $500, not an eighth of a dollar, but 500. So this would be what your the bank balance would look like. Yeah, now that's more like it. And you can see after 20 years, you've got around $1,200, $1,300. Your money is more than doubled. Okay, so in fact, about 22 years, you've tripled your money. So that's a nice little rate of return. And in fact, supposedly, now on average, if you look at all stocks in the US economy over the last 100 years or so, the average growth rate has been about 14%. Imagine what that would do to your balance. If you bought stocks instead of putting your money in the bank, whoa, look at that. Look at this. You can't even show it how much money you'd have after 20 years. It gives you something to think about, doesn't it? For 10 years, you've just about quadrupled your money. Wow. All right. Well, anyway, so now here we have some interest rate questions. Now, these are based on the formula, the future value formula. You might recall that there's 2 different formulas for future value. Future value tells me how much I'll have in my bank account in the future, given the interest rate that I'm earning and the time over which I'm holding this money. So we were introduced to 2 formulas. The first one I have to be careful here. R and N can look very similar if I'm not careful. Okay, so just a quick reminder, A is the future value. P is the principal, the amount that you started out with. R is the rate of interest, which is understood to be on an annual basis. N is the so-called compounding frequency. Which means how many times a year the interest is compounded or paid. So for example, monthly compounding means that N equals 12. Okay. And then finally, T is the time over which money is invested. And this is in years. And by the way, the interest rate here is also per year. Now, this is going to be true for all cases when n is finite. Okay, in other words, and typically in practice, that means anything up to daily compounding. This type of compounding is known as discrete compounding. Now, in the limit, as n grows and approaches infinity, the future value formula becomes, okay, A equals PE to the RT. Okay, so the only thing that's different here is this E. E is a constant that is approximately equal to 2.718. Okay, so now in Calc 1, they'll introduce this in a more formal way. They'll show you how it's derived. We don't have the background that we need to do this yet. But in Calc 1, they'll explain to you what E is and where it came from and why it's so important. But for our purposes, it's enough to understand what it is. And this type of compounding is known as continuous compounding. Now, in practice, you don't normally see this, but it has some very convenient mathematical properties. So continuous compounding is widely used in financial modeling due to its convenient mathematical properties. Now, you might say, well, why are we doing this? It's not completely accurate, but it turns out that you can convert between any two conventions without any real difficulties. In other words, if you assume continuous compounding and it turns out that the compounding is actually monthly, you can easily convert back and forth between the two of them to get your final result. So, all right, anyway, so that being said, here's the information we have. So we're told that we're depositing $10,500. That's our principal. It's a 10-year investment. The rate is 4%, but it's compounded quarterly. So what that means is this means that instead of paying 4% at the end of each year, the bank pays 1% every quarter or 3 months. And as we saw in the class, I mean, we know already that the more frequently interest is compounded, the more rapidly our balance will grow. Okay, so in other words, as n increases, future value also increases. So if you're the saver, you're investing the money, this is making you very happy. You're like, wow, if they keep increasing the compounding frequency, I'll earn more and more money. The person who's not happy is the borrower, because the borrower then has to pay more interest if it's compounded more frequently. So it cuts both ways. If you're the borrower, you want frequent compounding. If you're if you're the borrower, you want infrequent compounding frequencies. If you're the lender, you want the opposite. So in this particular case, we're going to plug in these numbers. Remember, A equals, because this is discrete compounding, which means we have 1,000, 10,250, Okay, so if you go to your calculator, what you're doing is you're multiplying the principal by 1.01 to the 40th power. And you should have approximately, and you can round this to dollars and cents, 15,260.85 in 10 years. That is what we mean by the future value. All right, and that's all you have to do. So compared to what we were just doing, this is pretty straightforward. I think you'll agree. Now, part B, they're asking us to change the compounding frequency to monthly, which means that n is 12 instead of 4. Okay. So we're going to just change that. I'm going to recycle what I've written already, which it's kind of nice if I can do that here, not on the board, that's for sure. So remember, you're changing the n. There's 2 n's in this formula. Don't forget, there's 2 of them. Okay, so what does that leave us with? So now 0.04 divided by 12, it's not going to be an even amount. You can round it if you want to, considering that we only need to know this value to within dollars and cents. This is probably enough. I'll tell you what, let's do a couple more. Now, you don't have to approximate it, by the way. What you can do is do something like this. If you're using the iPhone, that should do it. All right, I'm going to double check that on mine. Now, if you have a more sophisticated calculator, like the Texas Instruments series, it may be slightly different, but the logic is exactly the same. So within dollars and cents, this is what you should get. Now, with the other approach that I'm showing you, you need a lot of parentheses, unfortunately. But it does work. I'm doing it right now. And yes, it'll give you the same thing. So what they're trying, what the point of this question is to say that when n equals 4, A is equal to 15,260.85. When n is 12, A equals 15,281.03. And as we predicted, when n goes up and nothing else changes, the future value also goes up. So if we change this to daily, for example, it would go up even further. So this is what we're after here. So here now in 7, what they want you to do is go back to the original question, but change the time from 10 to 20 years. Okay, in other words, they want you to take this and instead of 10 years, it becomes 20 years. So there's only one change here. Now, I'm sure you can imagine that you're going to end up with a lot more money after 20 years than 10. The question is how much? Will it be double because it's twice as much time? Let's find out. So I've got 22,000 rounding to dollars and cents. $33. So originally, when t equals 10, with a 4% rate of interest, we ended up with 15,000. $260.85. So it didn't double, but it went up quite a bit, didn't it? Oh, wait a minute. No, hold on. Yes, no, that's right. Yes. So in other words, I want to make sure I didn't copy the wrong one. Yes. Our original assumption was quarterly. So that's 15,000. Yes, that's the right one. Okay. So it went up quite a bit, but not double. Because what's happening is that as time elapses with the same interest rate, the balance in your account is growing and will eventually reach a very high level. I'm sorry, this is not right. It's more like that. So in other words, here's 10, here's 20. And then as you keep increasing it, it'll continue to grow more quickly. So as you get further out into time, the amount of growth will continue to rise because you're being paid interest on a progressively larger balance. Okay. Now, here's, oh, this one is slightly different than the others. So it's basically the same thing with slightly different numbers. So let's just get the data together here. So here we know that a deposit is 6,500. 3.6% per year is the annual rate of interest. And by the way, if you notice with these types of formulas, you should never use the whole numbers. 3.6% should be converted into the decimal equivalent, which is 0.036. Now, we're assuming that this time compounded semi-annually, which means twice a year, and the money is left there for 20 years. 6,500 we can simplify this as 6,500 all right, so just multiply that out. And by the way, when you're doing this in the calculator, you might not necessarily want to go from left to right. You can do the 1.018 to the 840th power first, and then multiply whatever that is by 6,500. I've got 13,268.58. So you've doubled, roughly doubled your money. All right, so I noticed there weren't any questions here about continuous compounding. So just remember, if you do run into one, you're going to use this formula. This one. Okay. But for our, it looks like all of these are discrete compounding. All right, now with these, you're just literally going into your function and you're replacing the x with this value. Okay, so in other words, so if you want, you can rewrite this as 2 over.
I'm sorry, I just have one question. For
Yes.
continuous compounding, it would be PE and exponent RT.
That's
and then,
correct.
And then discrete would be the usual A equals.
That's right. That's
Okay.
right. Yeah,
All right,
that's the
thank
key
you.
difference. Yes. This continuously compounded form is actually a little bit simpler. But just find the e to the x key on your calculator, and then you'll be all set. Like, in fact, I'll tell you what, why don't we make one up right now just to make sure we're all ready for it. Suppose that an investor deposits $10,000 into a bank account that pays 5% compounded continuously for 10 years. What will be his balance in 10 years? So we know that P is 10,000. R is 0.05. Now, N doesn't appear in the formula because N is infinity. So we don't, you can't fit that into the formula. So what you're basically trying to do is, first, you always simplify whenever possible. So what I recommend you do is find on your calculator the value of e to the 0.5. And then whatever that is, multiply it by the 10,000. So now you want to make sure you know how to do this on your calculator. On the iPhone, what you're going to do is type 0.5. And then the e to the x button is sort of in the top center. And when you hit that, it automatically comes back with approximately 1.6487, let's say. And then, of course, you multiply that by 10,000 and hit equals to get 16,487.21. Now, on the TI-84, which is the only other one that I really know, I'm going to get my calculator out. Hold on. It's going to be different. I believe in this one, you have to do e to the x first. And on this calculator, you obtain this by second natural log. And it's going to show in the window e with a little exponent. So you then type 0.5 and then enter. Or again, 1.6487. And then of course you multiply by 10,000 equals, which leaves us with the same thing, 16,487.21. Okay, so whatever calculator you're using, be prepared to solve for e to the x. Okay, just in case you need it. And if you're going on to Calc 1, you'll see e all the time. All right, then. So here we're just evaluating these exponential functions. So here, what I've done is rewritten this algebraically, 2 over 5 cubed. Now, 5 cubed is 125. So what you could do is leave it like this, or it turns out this is equal to exactly 0.016. Okay, no problems there. Beautiful. So what do we have here? -1. Now remember, all the x's are becoming -1s. Okay. So you just have to be careful, that's all. And if you're not sure, of course, you can always double check. You just plug that back in and see what you end up with. Okay, now how about, oh, here we go, e to the x. Nice. And again, you can just leave it like this. You often see results written as e raised to some power, but if you really need to know the exact value, go to your calculator and you'll see that it's approximately 20.0855. Okay. Well, all right then. Now, what about this one? And again, you can leave it like that, but if you don't want to, if you plug these numbers in, it works out to negative approximately 27067, let's say. Okay. Very good. Now, we've seen this type of problem before. Foxes, okay. So we've got the years 2012, which we'll define as year 0, and 2020, which will become year 8. And remember, with these, we use slightly different notation. Not that it really matters, but it is nice to indicate that time is the independent variable in this case. So we're going to call it AB to the T power, and rather than using X's. Okay, so N of 0, according to this, is 23,900. Now remember, A is N of 0. In other words, the starting value. Now, this time, we don't know N of 8. But what we do know is that the growth rate is 9%. And since B equals 1 plus the growth rate, this implies that B equals 1.09. So that means we know already A and B. Okay, so A is 23,900, B is, 1.9, which means our function is 23,900 times 1.09 raised to the t power. But that's not what they're asking. They want to know what the population will be in 2020, or in other words, what they're asking us to do is evaluate N of 8. So therefore, oops, what am I saying? It's 2020. That's right. Because it's 8 years in the future. We're assuming that today is 2012. So therefore, all we have to do is plug them in. 109 raised to the 8th power. And so all you have to do now is solve for it. So I think, again, I recommend on your calculator, you multiply 1.09, or take 1.09 and raise it to the 8th power first. And only then do you multiply by the 23,900. I just think it's easier that way. So you're going to get 23,900 times approximately 1.99256.3, let's say. And that's going to wind up with, and by the way, this is a case where you have to have an integer. So you don't have to be overly precise. Because they're foxes, not, dollars. Okay. So in a case like this, you're going to round it to the nearest integer. When we have prices, we can round it to the nearest penny. All right. Well, that was interesting. So they gave us the starting point and the growth rate, and then we figured out the final value. So in other words, you could be potentially given any two pieces of information and ask for the third one, right? It's possible that they might actually ask you for the initial value too. In other words, you could be given N of 8 and the growth rate and asked to solve for A, the initial value. But here it didn't work out that way. Now, here's another one. Now, by the way, I just realized it doesn't explicitly say that we're assuming exponential growth. It should say that in the question. I'm going to make a note to myself. So I'm going to write this down in here. I mean, it's a good assumption given that that's what we're working on, but to be technically correct, I should have specifically said that it is growing on an exponential basis. So that way there's no doubt in your mind what you're doing.
I have a question.
Yes, go ahead.
How do you know that you're not going to use the compound, the continuous compound?
Well, this actually is continuous compounding. Okay, in other words, the growth rate is being compounded continuously. That's what an exponential function means, that the growth is continuous. So
how do
it's
you
implied.
know not to use the A equals PERT formula?
No, that you would have to be told what the compounded frequency is. That's how you would know which one to use and when. Okay, in other words, in these cases, it specifically says, for example, that the compounding is quarterly, and that's how you know to use this formula. Only if it says continuous compounding do you use this formula right here. This is only reserved for continuous compounding right there. If you notice, it doesn't tell you how frequently it's being compounded. The words continuous means n is infinite. Okay. So, and if I mean, if this is a test, you can come up and ask if you're not absolutely sure which one it is. It's, the point of this is not to make the wording confusing. It's supposed to be as clear as can be what you're supposed to do. Now, this one, we're going to use, remember we used, not that it really matters. We can use n. And in the slides, we use v for this topic. It doesn't matter. Let's just stick with n. N of t. I just realized that right now. As long as it is an exponential function, what letters you choose is not relevant. But what they're telling us here is that 1985 will be the initial value of 110. (2005) would therefore be t equals 20. Oh, so this is very much like the last one. Oh, no, it's not. Sorry, this one was asking for the future value of the fox population. Here, they're asking us what the implied growth rate is. Okay, so what do we know? We know that A is 110,000. Then we have B to the T power. But we also know that N of 20 would be 110,000 B to the 20th power, which in turn is equal to 145,000. So that means we can use the second equation to solve for B. We have A, we just need B. And remember, B is 1 plus the growth rate. So we're actually solving for B minus 1. So we divide both sides by the 110,000. So 145,110 is 1.3918. Approximately, that's close enough. So therefore, B is this raised to the 1/20 power. And as far as your calculator is concerned, what you could actually do is solve this as 1.31918 raised to the 0.05 power. Okay, it might be a little quicker because 1/20 is 0.05. All right, let's try that. So it's approximately 1.0139, let's say. That's good. So B is that. Now remember, B is 1 plus the growth rate. That means the growth rate, algebraically, is B minus 1, 1.0139 minus 1. Point 0139 that means the annual growth rate of the value of the house is about 1.39% compounded continuously, because this is exponential growth. That's not great for housing, by the way. In real estate, I would say the growth rate is a lot faster than that, but let's just say this is what actually happened. This is a part of the country where housing prices are just low for some reason. Maybe it's Idaho and hardly anybody lives there. So the value of the housing hasn't gone through the roof like it would have if this was purchased, let's say. All right. Now, oh, here we go. Referring to problem 14, what would be the predictive value in 2010? All right. So what they want you to do is take your formula. Now, we know what A is. That was 110,000. And then B is approximately 1.0139. When we raise that to the T power. And because the first year is 1985, (2010) would be year 25. And so what we need to do is solve for n of 25. Okay, so 1.0139, we'll do that first to the 25th power. That's going to be approximately 1 point, I have 41214, let's say. Oh, that's good. Especially since we're rounding to dollars and cents anyway. So we'll call this 155,335.51. If you got something slightly different, it shouldn't be off by more than a penny, let's say, depending on how much you rounded it. Okay, so give or take a penny, that should be your answer. All right. So these aren't that bad, are they? No. Now this one is interesting because now all of a sudden we have an asset whose value actually declines over time. It's a car. The value depreciates, as you know, because it gets used up. The more miles we put on it, the less it's worth. And even if you leave it sitting in the garage, it still loses value. The question is how much? Okay. It loses most of its value within the first 4 or 5 years, I guess. After that, the rate of depreciation falls off very slowly. So the difference between, let's say, 2 and a 3 year old car is pretty significant, but the difference between, let's say, 7 and 8 years is very, very little. So once you get to that point, you're just trying to hang on to it until it, you're trying to save money by not making car payments if you still have it after 8 or 9 years. All right, well, anyway, so we'll use the same setup. And let's just, NT, whatever. It's an exponential function where the independent variable is T. So it appears that the initial year is 2007. And we're being told that its value at that time is 38,000. That's our A. In 2013, the value is only 11,000. All right, so we're asking for a prediction for year 2017. So what that means is we have to figure out the value of B. So we do know the value of A. You also know the value of N of 6. All right, so here we go. All right, and you can see already that B will be less than 1. And that implies a negative growth rate in the value of this car, which is, of course, exactly what you'd expect given that its value declines. It's not like putting money in the bank where the value grows. The value is declining. But of course, you're also getting the usage of the car in the meantime. So it's approximately 0.81333, let's say. Now, what they're asking for, what is it worth in 2017? But in case you were asked, it doesn't ask for this. But if it did, this is how you would answer it. So in other words, the car is losing 18.667% per year. Okay. And so your function is actually now equal to so that's the function. Now they're asking us for the value in 2017, which is N of 10. All right, so I think your best bet is to calculate 0.81333 raised to the 10. And when you have that, multiply by the 38,000. And I have 48, rounding it to dollars and cents, it's approximately 4813.55. Okay, in other words, it really is losing a lot of value in a hurry. Some cars, as you know, depreciate more quickly than others.
I'm sorry, I'm just a little confused how it was to the 10th power. I guess I'm
Oh, because the current time is 2007. That means T is 0. In 2017, that will be defined as T equals 10, where we interpret that as 10 years in the future.
okay. Thank you.
Right. So in other words, don't use the year in your formula. You always use T, where it's 0 today, and this number reflects how far in the future you're looking. If you use these numbers, you will never get the right answer. Okay. So make sure you're using T rather than the actual time. Okay. So again, this number you could be off of, let me just double check this one real fast. So I think I may have over-rounded it a bit. I've got 30, not 40 cents this time, but all right, that's fine. All right. So, oh my God, that was that one. So that problem set is done. Ooh, what an ordeal that was. So now, yes, I will be posting this on Moodle when we're done. In this version, I mean, I have it all typed up, but I want you to have this one because I've written in a bunch of hopefully useful information to give you more explanation as to what we're actually doing here. So that's a disadvantage of writing on a whiteboard. It disappears. This doesn't disappear. This is one of the really good things about online that we can read. And not only that, but you can watch the recording. And if you miss something, you can just go back and watch it again. It'll be, oh, by the way, that reminds me, since this is our first time, I discovered this several years ago. When, during the COVID, all of our classes were online, as you can imagine. And so I was doing this every single day. And what we determined is that for whatever reason, Moodle doesn't seem to have a whole lot of storage capacity. And these videos apparently take up an awful lot of space. So what I had to do as a compromise is put it on my YouTube channel. And I will do the same thing here, but what I will typically do is, in order to avoid having you sort through millions of videos, which, my videos are all still sitting here from the past few years, I've created what are called playlists, which you are probably more familiar with than I am. And so each class gets its own playlist. Now, oh, I see what happened. See, that's this class from last fall. So it looks like I need to create a new playlist for this class. And then when I do, I'm going to post this video in that playlist. It'll say Math 1150 Wednesday, Spring 23. And this is probably the only video that we'll actually have there. But this way you'll know where to look for it. And I assume you're all very high-tech savvy, that you know how to find this. I don't know what information you need to find it. Either this thing right here, or else I suppose my name will do the trick. But there could be multiple Alan Andersons on YouTube. So I guess that if you search on that symbol there, that will tell you where to find it. So yeah, I've got all these videos in here from past years, and it's just like, ooh, it's a lot. And I had to delete some of them too, to avoid running out of space. Oh, it's a lot. Look at all this stuff I have. Oh my God, there's so many videos. But that's what we had to do. So I believe now, by the way, if you see a video you're interested in, you can feel free to watch it. I made them all publicly available. The only one I think that's private, the videos that I liked, like when you watch a YouTube video, you can hit that little thumbs up thing, and it keeps track of it for you, which is kind of nice. But by default, it's private. I guess you figure you don't want anyone else to know what music you're listening to. So I didn't fool with that, but the rest of it is public. Okay, it's just all, class videos. Okay, all right, anyway, so now you know. So now it's time for number 2. And like I said, I'm sure you all know infinitely more about YouTube than I do. It's just, I do use it, but I mean, I'm sure there's lots of cool things that I don't know about. You can actually make money when you put videos on YouTube. There's a way you can actually charge for advertising or something, which I don't know if any of you are actually doing that. Not me. This is all free. So anyway, let's try these. Especially people who are like musicians or, artists or whatever, they may have their own channels. But all right, anyway, we're going to take these logarithmic expressions and rewrite them as exponentials. Okay. Now, you notice here, there's a bunch of variables instead of numbers, but don't be confused. The principle is exactly the same. So for example, here, this is equivalent to saying okay, in other words, you have your base, this is your exponent. So an equivalent would be something like this: log base 4 of, let's say, 16 would be 2, which is equivalent to saying 4 squared is 16. I do think it's easier to deal with this with actual numbers. That means this one is a to the c power is b. And, they're all based on the exact same logic. Let's say log base 5 of 125 is 3, because 5 cubed is 125. Okay, so it's the exact same principle. And here, this one implies that 16 to the x equals y. And, these examples on the side are not necessary, but I just want you to see. Some real numbers. Okay. So essentially, one is just a transformation of the other. Oh, let's try a tricky one. Now, this one is tricky because ln is simply shorthand for log base e. Okay, so we'll run into that later on. Okay, now here we're just working it backwards. We're starting with an exponential and turning it into a log, right? So for example, this first one indicates that the log, the base 4 of y equals x. Okay. So these mean the same thing. And then in a very similar way, okay, so again, you've got your base, and this is your exponent. Okay. Now here we're going to have log e of h equals k, but you would normally write this as ln h equals k. Ln, remember, stands for natural log. We don't normally pronounce it ln either. It's understood. You just say the word log. Okay, and then this last one means that log 19 of y equals x. And again, it's simply another way of expressing the same information. Now, this will prove to be very handy when we're solving for actual equations because we can often rewrite these in a more convenient format. Okay, so for example, this one, now log 3 of x is 2. You might say, all right, what am I supposed to do with that? Well, your best bet is to say, wait a minute, isn't it true that this is the same thing as saying that 3 squared is x? Remember, this is the base. And this is my exponent. And now look how easy this is. This implies that 9 equals x. I don't know what else you could do with this thing. Well, technically, I mean, if you really, what you actually are doing here is this. You're taking this log 3 of x, but I don't think this is the easiest approach. And if you take 3, each side, we have 3 raised to that exponent. Based on the properties of logs, it's the same thing. But I think you'll find it easier to simply convert it. Okay, in other words, take this and turn it into this. And then go through this. This is a mess. But it does technically work, but I think you'll find it easier to do this. So like for this next one, this implies that 2, the minus 3 equals x. This 2 is the base. And negative 3 is the exponent. And then 2 to the minus 3 is 1 over 2 cubed. And that in turn is 1/8. Now, what if you say to yourself, I don't know if I did this correctly? You could try to do this in your calculator, but just be aware that your calculator doesn't have base 2 on it. So there's a workaround for that, but you're probably better off just going and doing it this way. Okay. Now for this next one, okay, once again, this is the base. This is the exponent. And that tells me that 25 is x. Okay. And now, this last one means and 3 to the third is 27. Okay. Ouch. So we have to be careful with these. Now for these, we're going to do some algebraic simplifications. So let me just quickly review with you the properties of logs. Now, if you notice, by the way, there's no base listed here because, well, at least these two. It's understood that these two have the same base, okay? And so we don't really need to explicitly write it here when we apply our algebraic simplifications. The ln logs, they're the same as well. So as long as these all have the same base, we can use the following rules. The log of a product is the sum of the logs, number one. the log of a ratio is equal to the difference of the logs. And the log of x raised to the n power is n times the log of x. So that being the case, let's try these. So we can work this one backwards. In other words, we already have a sum, which means this can be rewritten as the log of 2x to the fourth times 3x to the fifth. And so I can rewrite that as 6x to the ninth. So you notice what we've done is we've taken this property. If the log of the product equals the sum of the logs, then of course the sum of the logs equals the log of the product. So this is what we mean by simplification. And by the way, you don't have to stop here. You could actually then turn around and rewrite this as 9 log 6x. Okay, because it means the same thing. And that's based on this last property. The one as far as simplification is concerned, neither one of these is really more simple, but I just wanted you to recognize that. Okay, you could stop with log 6x to the ninth. Now this next one is a difference. Same base. You have to have the same base. So what you could do is rewrite this one. Actually, since this is a ratio, I'm going to do it by hand. I have an equation editor here, but it's not working correctly right now. Of course, like all technology, it decides to fail me on a regular basis. And yesterday was its turn to fail me, so I'm not going to use it today. So you can see 6 over 3 is just 2. X to the ninth over x squared is x to the seventh. And of course, if you wanted to, you could rewrite this as 7 log 2x. Okay. Nice. Now C. Oh, okay. Now here it's getting a little trickier. Here's what you might want to do. So what I've done is I've used this property. And now I'm going to turn this into a product. And yeah, if you want now, I think you can leave it like this, but in principle, what you could do. Now let's just leave it. I don't think it's worth a while to make it any messier than it is. But well, all right, I'll show it to you anyway. What you could do is rewrite this as 2, 3 log x squared. It's not x squared, x Because what I did was I reversed this rule again. So you actually could write it as 6 log. And this is actually just x squared plus x. And then, well, yeah, okay. So you can leave it like this. We don't want to get it too complicated. We're just trying to simplify it a little. But this is fine right here. This one here. And then D, oh, we've got a few things going on here. So you could rewrite it like this. And then if you notice there's a sum and there's a difference, so you could end up with the ones that are being added go in the top. And the one that's being divided goes on the bottom. Yeah, that's fine. All right. Now, this is where the properties will start to really pay for themselves. Okay, we're going to take some horrible looking equations and we're going to solve for them using the properties of either the logs, who we know, or exponential functions. So what about this one? Well, you've got an exponent on the left. The variable is in the exponent. What do we do? Here's a possibility. And it's not the only one. We're going to try this. Since this is the base here is 9. I can write this without changing the value of the equation. I can take the same log of both sides of an equation without affecting results. Just like I can double both sides, or I can cut it in half, or take the square root of both sides, as long as I do the same thing. Now, why did I do this? Because, first of all, the log to any base of 1 is just 0. And the log to any base of b to the x power is just x. Okay, just as a quick example, log, let's say base 10 of 10 to the 3rd power is just 3. You can think of it as almost the log is offsetting this base, and what's left is simply the exponent. So what that implies then is that we'll take this expression, copy it down here, and what that means is that all of a sudden, all I have is x minus 10 equals 0. Ah, that's it. Now, what if you decided, you know what, I'm really not sure if I did this right. Let's double check this. Is it true that this gives me the correct value? So what I'm asking then is 9 to the 10 minus 10 power equal to 1? Well, that's 9 to the 0 power equals 1, or 1 equals 1. this proves that x is equal to 10. So in case you had any doubts in your mind, well, now those doubts have been resolved. This is definitely the correct answer. All right. So whenever you see something like this, you have an exponential function on one side of your equation. The first thing you want to think about is logs. So is there anything we can do with the properties of logs to simplify this? And the answer is almost invariably yes. All right. So that's our strategy with these exponential functions. Think about using logs to simplify them. And similarly for b. Now remember, e here is the base. ln equals log base e. So what I'm going to do here is take the log of natural log of both sides. Okay, now what I might want to do to is rewrite this as just to keep it as simple as possible. So I subtract that log 2 from both sides. And now, if you want, you can combine these using the properties of logs. And now you notice log is base e, so this reduces to 6x. And now all I have to do is divide out the 6 from both sides. And I'm done.
I have a question.
Yes, go ahead.
Could you have divided by 2 in the first place, like before you even started?
Yes, I mean, because what you're actually doing though is you are subtracting. So, I mean, it amounts to the same thing. Yes, I mean, technically what you've done is equivalent to dividing both logs by 2. But I don't know, I prefer to do it this way because it explicitly shows you the properties of the logs that we're using. But yes, you could have divided both of these logs by 2 because they have the same base and you would get the same result. So anyway, let's try this one. Now, something like this, you should probably simplify it before you attempt to do anything else. In other words, don't leave it like this, because you'll just end up with a mess on your hands. Why don't I add that e to both sides first? And let's divide out that -5. That pesky -5 is not doing us any good. Okay, so of course that means we actually have positive 54/5. Now I'm going to take the natural log of both sides because e is the base of natural log. So you got to make sure you choose the right base. Otherwise, you're not simplifying anything. Okay. And now this implies that 9x minus 8 is the log 54/5, which is a constant. So what I can do is add the 8 to both sides like I normally would with any other algebraic case. And then divide by 9. And that is just some constant or other. I don't know exactly what it is, in fact, but we could figure it out. Log of 54/5 plus 8 divided by 9 is approximately 1.15. So let's say this is the price of something. You're trying to figure out the right price to charge for some product or other, and this is the formula that you use. Then that means the correct value is about $1.15. Now here, the same thing. Don't just leave it like this. Clean it up. Subtract the 2, divide by the 10. Now we'll take the natural log of both sides. We're using natural log because the base is e. Okay, and so that implies that 8x plus 3 ln log 0.6, subtract the 3, divide by the 8. So yeah, once again, I mean, it's a very, very messy expression. So I'm just going to quickly throw it into my calculator. Just in case you want to know the exact value. It's approximately negative 0.4389. Okay, great. And now one more. Again, it's E. So we'll have add the 7 to both sides, divide out the 4. Take the log of both sides, of course. All right, and again, if there's some reason why you must know the exact value, like this is the solution to some problem you're solving for a price or a weight or whatever the case may be, the log of 15 minus 3 divided by 3 is approximately negative 0.097. Okay, you don't need to do that though. 1/3 of log 15 minus 3 is fine. So there's a couple of more blocks of problems here involving logs and exponentials. And ooh, I see it's awfully close to 10 o'clock, our traditional break time. So we'll do the usual routine, a half an hour or so, to get refreshments in your system because this is very challenging material. And then when we get back, we'll wrap up these two, and then we'll at least go back and start to revisit chapter 5, which is our overview of trig functions. Okay, so we'll cut it off. We'll come back around 10:30, and we'll take it from there. Okay, now since you're in your room or home, it might be easier to get food than normally it would be in our room. We have to run quite a ways to get there, but anyway, so see you all in about half an hour. Oh, all right, I guess we can get started again. So there's a few questions left, and then when that's done, we can go on and revisit. Oh, yes, we want to go back and pick it up where we left off with chapter 5. Okay, our introduction or overview, at least, of trigonometry. All right, so let's get back to this. Now, these again are going to depend on the properties of logarithms. So, as always, you want to make sure that this is as simple as it can be before we do anything else with it. So in other words, here, what we should probably do is divide both sides by 5. So we have log base 7 of x equals 2. Now remember, based on the properties of logarithms, we can rewrite this now in exponential form as 7 squared equals x. And therefore, we end up with 49 equals x. And that's it. That's all you had to do. So the key to the whole thing is rewriting it as an exponential function so we can more easily calculate it. Okay, and then we're going to see something similar in every one of these cases. So here, for example, we'll divide out both sides. Okay. All right. Divide out by that -8. And so we have log base 9 of x is -2. But again, we can rewrite this in the exponential form 9 to the -2 power equals x. And of course, this is the same thing as 1 over 9 squared. And that means we have 1 over 81. All right. So what else do we have? So for this one, let's do some algebra first. Subtract the 4 from both sides. And then in exponential form, this is 2 to the -2 equals 9x. And this is the same thing as 1 over 2 squared. We'll multiply both sides by 4. And now we'll divide both sides by that 36. And here we go. All right. And then one more. Two log base 2, 8x plus 4 plus 6 equals 10. So we subtract 6 from both sides. Then we divide by 2. Now, knowing or using or converting this into an exponential form, we have 4 equals 8x plus 4. Subtracting 4 from both sides, 0 equals 8x. And finally, when we're done, we end up with x equals 0. All right. Now, and then finally, these, they're very similar to each other, but here we can take advantage, though, of a result that we had in the class. The so-called one-to-one property tells us that if, for example, we have the log to base b of, let's say, x equals the log to base b of y, that implies that x equals y. Okay, so therefore, since we have the log of natural logs on both sides, this implies that 10 minus 3x is negative 4x. And we add our 3x to both sides. And that means that negative 10 is x. Okay. Now, let's see what else we have. So for this, based on the same logic, this one implies that negative 3x equals x squared minus 6x. Okay, so let's see, let's add the 6x to both sides. And then divide out both sides by x. No, that's it, we're done. Wow, but that was easy.
Can you go up one slide, please?
Oh, sure, yes.
Thank you.
Okay, who about there?
Yeah, that's fine.
Okay, good. Yeah, this is the one thing that's awkward about being online. I can't tell if you can see what I'm doing, or if you're behind or ahead, or I don't know. I'm just hoping for the best. Are you ready?
Yes, I'm sorry. You're
Oh,
good.
it's okay. All right, good. All right, so we just have the 2 more. Now, oh, so now we don't have that same setup here. So here we just use the properties of logs. Okay, now remember, so this means that 2 to the 3rd equals 7x plus 6, because this is our base. And this is our exponent. So we don't have 2 logs equal to each other, but we can still take advantage of the properties of logarithms to do this. Subtract 6 from both sides. And now we'll divide both sides by 7. Yes, 7. Now this last one, we do have the same log on both sides, so we can just rewrite this as 6x, 6 minus x rather, equals 3x. So we add the x to both sides, divide out the 4, and we'll just simplify that as 3/2. All right. So that is it for part 2. So So far, so good. If you can do those, you'll be in good shape for the next midterm, whenever that shows up. And now we can get back. We started to briefly look at our trig functions last time, just a quick review. And so here we're going to do the same thing, but we'll maybe take it a little further today. All right, is everyone done? All right, so I'll open up chapter 5 now. All right, so basically we introduced some terminology last time. We didn't just review the basic trig functions. We also introduced some new terminology, but we also, well, all right, let's just quickly take a step back and quickly review what we've already done, and then we'll see what's coming next. But yes, we did see some very interesting things here. For example, the concept of a negative angle. So start by quickly reviewing the 6 basic trig functions. So the sine is defined as the opposite over the hypotenuse. So here's our triangle. Here's the angle that we're interested in. The sine, now the opposite side is here. This is the adjacent side, and this is our hypotenuse. So the sine is the ratio of the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. The tangent is opposite over adjacent, which, by the way, implies that this is equal to the sine over the cosine. Okay, now the other 3 are just functions of these 3. So for example, the secant is 1 over the cosine. Which is h therefore over a. The cosecant is the inverse of the sine, which implies that it's h over o. And then the cotangent, 1 over the tangent, obviously, which means that it must be a over o rather. And so that's how they're formally defined. Now, the calculators do have the ability to calculate these measures. I'm going to get my TI-84 out right now. And if you look at the buttons, it does say slightly above the number of keys, sine, cosine, and tangent. And so you don't actually need the others because we know they're simply inverses. So in other words, it doesn't have a separate secant key, cosecant key, or cotangent because it's understood how this relationship works. Right? We don't actually need them. They're redundant. And you know, on these calculator spaces that are premium, they're only going to include things that are absolutely necessary. Now, the one thing we do have to watch out for is that we're going to calculate these measures based on angles, but we're also going to eventually do what are called radians. Okay, now this calculator can do that, but you have to know how to switch it into radians mode. And the same thing holds, as I started to say in class, with your iPhones. They have a radian mode and they have an angle mode or degrees mode, where if you switch them back and forth, you can get what you're looking for. Okay, so we also formally define what we mean by an angle. Just the concept of an angle is an important idea. What you're basically doing here is you're taking 2 rays, they're called. And, you know, with a straight line, as you know, a straight line goes up, it covers the entire real number line. In other words, there's no starting point, there's no ending point. A ray is different. A ray has a specific starting point, but no ending point. It continues to go on either to positive or negative infinity. So if we combine 2 rays, or we find that 2 rays have a single common starting point, then theta could be thought of as the angle between them, or it could be formally defined as how much rotation is needed to move from one ray to the other one. And when we talk about rotation, we are thinking in terms of what proportion of an entire circle are we moving to move from one ray to the next, with the understanding that moving completely around a circle is 360 degrees. All right, so all these other angles are essentially proportions of that circle. If we have to move 1/4 of the way around a circle to reach the other side, like if we have something like this, then that would be 90 degrees. Because that's exactly 1/4 of a circle. Now, also, there's an implicit understanding that we're moving in this direction, counterclockwise. Oops. So the angles are defined in terms of counterclockwise motion. If not, if we're moving in the opposite direction, then the angles are defined as being negative, as we started to mention last time. But before we get to that, I just want to remind you that here it is. The vertex is the point. Where was I? Oh, here we go. So in the diagram, two rays have a common starting point. Theta is the angle between them. There's an initial side, a terminal side, and a vertex. In other words, we have to know which direction we're going in. Going from this initial side to the terminal side means that we are moving in a counterclockwise direction. So whatever angle this is defined to be positive. If we're going the other way around, then it is defined as negative. And a single degree is defined as 1/360th of a circle. Okay, now we're usually going to draw these diagrams with the understanding that our starting point is the origin. Okay, in other words, this point right here is the origin. It's the point 0, 0. I mean, in principle, I guess we could use other starting points, but we normally will start with the horizontal axis and we'll move from there. Okay, the common point between the two rays that we're describing is going to always be the origin. All right, so I mean, it's like I said, there could be other situations, but for our purposes, we'll always stick with these basic cases. And if that's what we're doing, we said that the angle is in the so-called standard position. Okay. So again, we have an initial side, a terminal side. We move counterclockwise. And then what we're basically measuring, the angle simply represents what proportion of the circle does this represent, with the understanding that each quadrant contains 90 degrees. So in this case, it looks like we're going through the entire first quadrant and about halfway through the second quadrant, which means that we have 90 degrees here and 45 degrees here. And if that's the case, then this theta would be 135 degrees. All right, so it's like whatever proportion that is of 360. So if we move the opposite way, we'll end up with a negative angle. Now, let's see if I can draw this properly. Oops. I'll tell you what, let's see. Now I can draw this with different colors. I just haven't been. This to be consistent, let's use blue. So basically, if we are moving in the counterclockwise direction, as I just mentioned, this would be 90. This is 45 for a total of 135. But if we're moving in this direction, you can see that we traveled a different distance, didn't we? Here we had 90, we're moving all the way through the fourth and third quadrants, plus another 45 degrees into quadrant 2. So these add up to 225, but because we're moving in the opposite direction, we call this a negative angle. I mean, we can't call it positive 225 because that would mean there are two different ways of defining 225. So instead, we'll think of this as a negative angle. And if it gets confusing, just keep this in mind. If you notice, the absolute values of these two will always add up to 360. Okay, so in other words, you immediately know, if you know the positive angle, the negative can be obtained from this relationship because the absolute values have to add up to 360. All right, now also, we'll get to this in a bit anyway. I just want to mention that what happens if you go around more than once? In other words, let's say I've done this. So I'm going, let's say, here's the terminal side, but I'm actually moving all the way through the full circle and then coming back to this point. Oh, now that's interesting because I've gone around the entire circle plus another 45 degrees. Well, in that case, the angle could be thought of as world 5. So what that means then is that these two angles actually mean the same thing. They both bring us to the same starting point. Okay. And so if I went around twice, that would bring me to a total of 405 plus 360, which would be 765. And again, it means the same thing. So the angles larger than 360 degrees are not unique. They're equal to a smaller angle, which is less than 360. So basically, we only really need to focus on the angles that are less than 360. The larger ones can be converted or are equivalent to the smaller ones. So there's a terminology for that. These two angles are said to, oh, wait a minute, no. These angles, yes, these two angles are said to be coterminal. Why? Because they both have the same starting point, but they also have the same terminal side. It's just that one of them got there from a different direction. So they both wound up in the same place. So they represent the same thing, except that in one case we went clockwise, the other is counterclockwise. Either way, we wind up at the same terminal side. So they're called coterminal. Okay. All right. Now, here's the one. I always found this to be a nuisance in high school. The concept of radians, I still to this day, I'm not sure why one would use radians instead of degrees. There must be some applications where it's easier, but it's kind of, it's almost like having to constantly switch back and forth between Celsius and Fahrenheit. It's really kind of a nuisance, but we have to be familiar with both ways of measuring angles. A radian is simply equal to, it's approximately 57.3 degrees. The numerical relationship is this. 2 pi radians is 360 degrees. So in other words, going around the entire circle once can either be thought of as 360 degrees or 2 pi radians. So all the radians are measured as a function of pi, as opposed to degrees. So here's a little chart to help us get this straight. But if you notice in all these cases, like these fractions, in order to get this pi over 2, what you actually did was you took, so in this case, if pi is 180, pi over 2 is just 180 over 2, which is 90. Okay, which means, of course, that pi over 3 is 180 over 3, which is 60, et cetera, et cetera. So you might be better off thinking about this relationship to help you remember how to convert radians into degrees. Pi radians, 180 degrees, is the same thing. I don't know if the calculator can do that conversion for you. So this is something we might want to just remember. All right. So for example, pi over 6 radians is very simply 30 degrees. So all you're doing is you're taking the 180, dividing by 6, and you get your 30. So in other words, think about it this way. Pi equals 180 degrees. Pi over 6 must be 30 degrees. Okay. About 3/4, no problem. So 3/4 of pi would therefore represent 135 degrees. Okay. And now the next slide, just we've already discussed this. These two angles are defined to be coterminal because they both have the same initial side. They both have the same terminal side. So they are the same angle because they bring us to the same location. But here, going in a counterclockwise direction, we're going through 90 degrees in the first quadrant, 50 degrees in the second quadrant. Here, though, we're going through 2 quadrants and 40 degrees into the third quadrant. So 90 plus 90 plus 40 is 220. And this, of course, is defined as negative because we're moving in the counterclockwise direction. So we call these coterminal because they both bring us to the same terminal side. And remember, once again, their absolute values will give us 360. Okay, so that's the way. If you're not sure, just you can draw the picture, or you can just see whatever number has an absolute value, which brings the total to 360. Now we also have the concept of reference angles. By the way, you might remember from high school geometry, the word acute angle means an angle that's less than 90. There's a whole slew of adjectives that we can come up with for these angles. Maybe we'll go look them up. So acute means less than 90. I'm starting to forget some of the other ones, so let's go double check. Here we go. I knew some helpful person had made a chart like this for us. Okay, right angle is, of course, 90. Obtuse, there we go, is between 90 and 180. I see what they've done. Actually, so what they're saying is that a right angle is equal to 90. Obtuse, then when we get to exactly 180, they call it a straight angle. Actually, I should have written it like this. because it's just a straight line. Reflex, I was not familiar with that one. Is greater than 180. But of course that means it's also, actually, let me write it like this, just to be consistent. And then they're calling a full rotation. Exactly 360 degrees. See, this happens sometimes in here. It's very annoying. Oh, there it goes. That little box that had a label in there. Okay, so in case you forgot, just a little refresher. These are the formal names or adjectives for these angles. Okay, so I think this is very helpful. Hold on one second. All right. Now, how do you find a reference angle? Now, remember, it did say that a reference angle is an acute angle, the smallest acute angle that can be formed from the terminal side and the horizontal axis. Okay, so in other words, let's say, so anywhere in the first quadrant, let's say the angle is 80. Then you would have your reference angle would be 80. Over here, though, let's say your angle is 135. That's going to be 45 degrees. Why? Because, oh, okay, that would be here. And so basically the way to think about it is that to get to this point, you went 90 degrees to the first quadrant and 45 degrees into the second quadrant. So what it's trying to capture is how far did you move into this quadrant? That's really what it's all about. And then let's say down here, you're at 225. That would be this. And so you're going to have 225 minus 180, which is again 45. And again, the way to think about it is how far did you have to move to get into this quadrant? And then let's say you have, this would be 315. Again, 45 degrees. So even though it's 315 degrees to go all the way around, you've actually had to move 45 degrees into this quadrant. Here, it doesn't matter. It's 80 degrees any way you look at it, because you only went through one quadrant. But after that, what you're really trying to do is keep track of how far did you have to move to get into that quadrant. Now, the same thing can be said about radians. It doesn't look like there's a chart here. That's interesting. Why don't we make one up then? All right, so with radians in the first quadrant, it's just the angle itself, which is no surprise. The second quadrant is pi. Now remember, this is the same thing as 180. Pi radians is 180 degrees. So that's why it's written this way. So that means in the third quadrant, it should be angle minus pi. Whoops. Which, I think that's a typo. Yeah, in order to be consistent, it would have to be angle minus pi. So I'm going to write that as angle minus pi. And then the last one to be consistent would be 360 minus angle, which is 2 pi minus the angle. So because it amounts to the same thing, going back and forth between radian and degrees is really no different than going back and forth between Celsius and Fahrenheit. So anyway. So here's an interesting example. 740 degrees, what would that be? We go around the circle twice. And then 20 degrees into the first quadrant. So for that reason, the reference angle is 20 degrees. Okay. But if you weren't sure, just be aware that if you go around the circle twice, that's 720 degrees. So these two are actually equal to each other. Okay. And therefore, since the reference angle is in the first quadrant, the reference angle equals the actual angle. Yes. Now, we're going to introduce a very important concept. What we're going to actually do here is start to understand how the trig functions are derived. In other words, why does the sine of 30 have a certain value? And why does the cosine of 60 have another value? We're going to show with geometry how some of these measures are calculated. We're going to start with this concept called the unit circle. And what this means then is that we're going to start with the origin at the center, and then we're going to choose a circle whose radius is exactly equal to 1. Okay, so remember the radius cuts halfway through the circle. The diameter cuts through the entire circle. And because of the way the circle is defined, the radius is the same no matter where we draw it. Okay, so here I've chosen this point. We have 0, 0, and the distance to the circle, to the perimeter, that is 1. And this is what we mean by a radius. How does that help us with the trig functions? Because what we're basically going to do is inscribe triangles into this unit circle, and we'll use those to calculate our sines and cosines. Now, this is a fairly involved process. We're just going to start it right now. We'll have to pick it up again next time because, this takes a little explanation. But we know that sines and cosines are defined in terms of a triangle. All the rest can be found in terms of the sine and the cosine. So now, once you know how to calculate the sine and the cosine, you can do the rest very easily. Okay, remember the tangent is just the sine of the cosine. The cotangent is the inverse of the tangent. The secant is the inverse of the cosine, and the cosecant is the inverse of the sine. So once you know the sine and cosine, you can figure out the rest very easily. And again, just remember that the sine is the opposite of the hypotenuse. The cosine is the adjacent over the hypotenuse. Now, of course, all of this requires us to remember our old friend, the Pythagorean theorem. Which is very simply so if the opposite side is 1 and the adjacent side is radical 3, this implies that the hypotenuse must be 2. Okay, so what we would like to know is the sine of theta and the cosine. So the sine of this angle, whatever it is, one over radical 3. Which normally you would rewrite that as radical 3 over 3. The cosine of theta, a over h, is radical 3 over 2. Oh, no, wait a minute. I'm sorry. I think I copied something wrong here. Yes, I did. Hold on a second. After all that. OH, yeah, sorry, my fault. This side A is the opposite. B is the adjacent and C is the hypotenuse. Yes. So I did have it backwards. Over H is 1 over 2. Oh, that's so much nicer. And then up here, the cosine is A over H, which would therefore be radical 3 over 2. So now with those in place, I can calculate all the others as well. So now this is where it gets interesting. This graph that we're about to look at. So you have to imagine that T now is the angle. We're facing the other way. Here's the right angle. So with respect to T, this is my opposite. This is my hypotenuse, and this is my adjacent side. So the sine of T, opposite over hypotenuse. Now keep in mind that this 1 is the hypotenuse. Okay, because, and also notice it's a right triangle. So what that indicates is let's see, where are we? So O over H, H is 1. If you look at this point, the height of this line is my y coordinate. Okay, in other words, the opposite is nothing but the y coordinate of this point. So this y is actually equal to the sine of t. And cosine is the adjacent over the hypotenuse, but since the hypotenuse is 1, that implies that the x coordinate is the cosine. See, this is, like I said, it's getting very complex now. And so what we're building up to here is that by defining this as a unit circle, where the hypotenuse is guaranteed to be 1, whatever angle t is, we can figure out its cosine and sine by simply looking at this point xy, because the x coordinate is the cosine and the y coordinate is the sine. And by understanding that, we can then in principle calculate any sine or cosine that we need using this graph. Okay, so now this is where it's getting very involved. Oh my God. Yeah, I'm scrolling ahead here and I'm seeing that we're getting in some very deep waters here. Oh my God. All right. So you know what? I know it's a little early, but I think we've done enough for one day because I don't want to rush through this part. I think we're going to have to pick it up again right here and start again with this unit circle, because this is a very complicated process. And so what it does is it gives us insights into how these cosines and sines are calculated. And so that's what this is all about. So, all right, I'm going to post the solutions so you can look at them as much as you want. And remember, we're off next week, so I won't see you for 2 weeks. So I don't want to start something now that you'll have to, you might forget in 2 weeks. So rather than rush through this, I think we'll stop here and we'll pick it up again in 2 weeks with this discussion about sines and cosines and the unit circle. Okay. So, all right, I guess I'll just, since I won't see you again, I'll wish you all a happy spring break and I'll see you in 2 weeks.
Thank you so much, Professor.
Okay, you're welcome. All right, see you later.
Thank you.
Bye. Oh, you too. Okay, thanks. Bye.
Professor, did you do attendance already?
Yes, we're all set. I took it. I have you.
Okay, okay, thank you, sir.
Okay, all right. See you next time.
See you. Have a good break.
All right, bye.
So hi, Professor. I just wanted to ask, you'll post the solutions, right? I emailed you
Yes.
about it, but
I will. Don't you worry. I'm up to my eyeballs in work right now, but I will get to it.
Okay, no problem.
All right.
And yeah, and then the next midterm is like April 5th, so it's a long ways away.
It's a ways. Yeah, it's quite a ways off. And it's not related to the first one anyway.
Right, it's only 4 and 5.
4
like,
and 5 only. Right?
basically what we did today on top
Yes.
of 5.
Right. Exactly.
That we'll review like in 2 weeks, right? Okay.
Yes.
All right.
Okay.
Thank you so much. I appreciate it.